Good morning or good afternoon, depending on where you're at. My name is Atarod Azizi Namini, and very warm welcome to IBT/ABC-UTC January 2025 monthly webinar. We are delighted to welcome more than 700 sites that have registered to listen to our January 2025 monthly webinar. We are delighted to bring to you this month a topic entitled Seismic Connections of Precast Columns to Foundation Utilizing UHPC. We are happy to have two great speakers with us, Bruno Massicot, who is a professor at the Department of Civil, Geological and Mining Engineering at Polytechnic Montreal, and Dominic Washon, who is a professional engineer and head of the bridge and tunnel department at City of Montreal. During the registration process, we have received a number of the questions that Paul and Rick Liptic are going to be moderating. They will get to it as time permitted, but it's not late during the presentation. If you have some additional question, please, by all means, post it on the dashboard, and we'll get to it as time permitted. This webinar will finish somewhere between 15 to 20 minutes after the hour, depending on the number of the questions that has been submitted and we have received. First of all, thanks to almost 600 people who attended our very successful 2024 World Bridge Engineering Conference just last December that was held in Miami. It was very well received, and we are happy to tell you that we have already set the dates for the 2026 World Bridge Engineering Conference. These conferences are held once every 2 years. The 2026 World Bridge Engineering Conference is going to emphasize innovative bridge technologies and accelerated bridge construction. It will be held on December 1st and December 2nd. It's going to be 2 days, December 1st and December 2nd, 2026 in Miami, Florida. We're going to be sharing with you much more information. Please, by all means, visit our website. We are going to be posting very soon when the call for abstract is going to open and some important dates. So with that, I'm going to turn it to Kathy, who is going to be sharing some additional news related to the bridge engineering in general. Kathy?
Great. Thank you, Torad, and thank you all for joining us today. I'm Kathy Kroll, the Co-Director of Technology Transfer for the IBT ABC UTC. Before we start the featured presentation, I'd like to share some upcoming events with you, but before, both from the IBT ABC and from our industry partners. The first event is the PCI, the Precast Prestressed Concrete Institute's 2025 PCI convention at the Precast Show. This is February 3rd through the 7th in Indianapolis, Indiana. For more information and registration, you can go to the link that's on the screen or contact William Nickus. The next event is the AISC NSBA, the American Institute of Steel Construction National Steel Bridge Alliance, will be having the Steel Conference, which includes the World Steel Bridge Symposium. This will be April 2nd through the 4th in Louisville, Kentucky. For more information and registration, the link is on the screen, or Vin Bartuka can help you with additional information. The next event is the ACMA, American Composite Manufacturing Association, will be having the Design Pulling Protrusion Conference in Chicago, Illinois from May 6th through the 8th. The link is on the screen. And now we will go into some of our own events. Our quarterly research seminar will be on January 31st. It will be on pre-stress losses in UHPC and hybrid precast pre-stress bridge girders. Royce Floyd and Omar Yadek will be presenting from the University of Oklahoma. Our next monthly webinar will be on Thursday, February 20th. Can you advance the slide? Sorry. There we go. Our next monthly webinar will be on Thursday, February 20th from 1 to 2:15. It will be on fast cast bridges for rural transportation solutions. We'll be joined by Anthony Vanneman and Christopher Swanson, who are both with Premier Steel and DCI Engineering. And we're very pleased to be joined by two partners from the Indian nations, the Muskogee and the Choctaw, to tell us about their experiences with rural solutions utilizing these fast cast bridges. One more webinar announcement. In March, also on the 20th, so March 20th, from 1 to 2:15, we'll be having a presentation on sprayable UHPC, and this will be on the Virginia DOT's abutment repair, and will also include information about the development of mobile capabilities. We will have Torad Aziz Namini, our director, will be presenting along with Sam Falaha. Please mark that one on your calendars. It will be a very interesting presentation. And that brings us to today's webinar. So before I introduce our presenters, I'd like to thank you all for joining us today for the 166th webinar in our monthly series. As many of you know, these webinars are recorded and posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation is provided in the Go-To dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. Please enter any questions you have in the question box in the Go-To dashboard. With that, we will now begin our featured presentation. We welcome Dr. Bruno Massicat. Oh, I had a power outage. Am I here? I think I am.
We can hear you.
Oh, I'm so sorry. There was just a power blip. It was very strange. I apologize for that. So let me back up. With that, we'll now begin our featured presentation. We welcome Dr. Bruno Massicat and Dominique Vachon, who are joining us today from Montreal. Bruno and Dominique, please turn on your cameras if you would.
Yeah.
Bruno and Dominique.
Can you see me? I'm not sure if my camera is on.
I see Dominique. I haven't seen Bruno yet.
Oh, okay. I have. Okay, sorry. I need better glasses. Okay. Oh,
don't we all?
Okay, I'm sorry. Okay, you should see me now. Okay.
There you go. Welcome, Dominique and Bruno. Dominique and Bruno will be presenting on a research project that has been implemented on a bridge project in Montreal. We thank you very much for sharing your time and expertise with us today. And with that, you are ready to begin.
Thank you, Kathy. Thank you, Hatrod, for this introduction, and thank you for the invitation. We're pleased to be joining you today. Thank you for everybody for attending. So thanks for IBT, ABC, UTC for this invitation. So I hope. Okay, everything's fine, sir. Okay, so the title of the presentation is Seismic Connection of Precast Column utilizing UHPC. And normally I will be handling the just a second. Okay, now it's okay. So the presentation, so the outline will first talk about the City of Montreal interest in ABC. I'll give you some background information on elements that are important to know for the other part, the technical part of the presentation. I'll talk about the concept, its development and validation, and we'll finish the presentation by talking about the pilot project. So Dominique and I will go back and forth. So that's Dominique's side time now.
Hi, everyone. It's a pleasure to be here. I'm going to do a fast overview of the interests for the City of Montreal in ABC construction. As you may or may not know, Montreal is one of the oldest city of North America, and we have a lot of bridges, 300 bridges, 5 tunnels, and also, we didn't mention it right here, but we have around 250 retaining wall and culvert. All of those are managed by my department, and a lot of those structure needs, since we're old city, we needs a lot of repair or replacement. So we see a lot of advantage in using ABC as a mean of construction. We have a lot of mobility issue in Montreal, so and a lot of work on road work. So a lot of construction cones everywhere, and a lot of the people living in Montreal are tired of that. So we really try to accelerate how we do our construction. Also improve durability. We're in a really harsh climate and we use a lot of de-icing salts, so we need to have more durable material to be used. And also we see as ABC as a good way to have innovation in our project. Our city has been involved with École Polytechnique for the last 20 years, developing UHPC application and also accelerated bridge construction. The first use of UHPC we did was we use it as a slab on a pedestrian bridge. And what is really nice about that is we got the same pedestrian bridge close by, another one, a copy of it, but with more standard concrete. And now we're following both of those to see how it goes. Can go to the next slide, Bruno. So in this presentation, we're going to talk about the underpass of bridge des Carrières in Christophe Colomb. It's situated in the middle of Montreal. And as you can see, the bridge needed a lot of repair. The barrier were really unstable. We had New Jersey barrier installed. We had a lot of degradation of concrete. So we needed to replace that bridge. Next. So we decided to, while replacing the bridge, we'll see the opportunity to replace and review the configuration to make it more safe for people. And as you can see, it's one of the main roads that goes under also the train tracks. So in Montreal, the train track traverse all of the cities. So that's one, those type of underpass, we have about 10 to 15 of those, and they all need repair. So this one was the first one we tried to replace. Next slide, please. So it's our first ABC project. As you can see, we tried to make it more beautiful for the people living in Montreal. It was really all concrete and really degraded. So we did a lot of architectural pattern, and we tried to make it a more livable space. Next. So when we go in ABC, want to do ABC Montreal, we decided to take that project because take that site. It's not a site where there's a lot of traffic problem. The roads end up near a park, so it's more of a local road, but still it represents what we're gonna have to do with the other underpass. And we didn't make it easy, so we took a complex geometry, curve and skewed. We did have a lot of similar elements, so the precast element were a lot of trouble. Also, we had the low clearance of the roadway, so doing precast was really interesting to get a better clearance. And we wanted to do 100% ABC for the bridge. Like you see, the abutment and retaining wall were kept, but the bridge was 100% ABC from footing to the barrier wall. That's it. And now I'm going to pass back the mic to Bruno.
Thank you, Dominique. So some background information. First, Canada. So Canada is north of the US, so you can see where we are. And some of you may ask, why is Seismic in Montreal? So this is a map of Montreal, and with the acceleration zones, where you can see that on the west coast, which is quite similar to the Seattle region near Vancouver, but along the St. Lawrence River, which we see here, you can have very high, it's a highly, or moderate to high seismic region. Montreal is right here, Ottawa, the capital, is there. So Toronto is not of concern. And that area, you can have very, very high seismic event at that location. The return period for seismic is about 150 years in eastern Canada. So, and it's 100 year this year. So since the last one, that's big one occurred. So we're getting ready for the next big one. What is UHPC? UHPC, for those who are not quite familiar, it's a it's a cement paste in which we put fiber. So the European call it UHPFRC, so which is the same as UHPC, which what we use in North America as an acronym. So its main characteristic in compression, it's about 125 MPa. I will be switching from SI to American units, but I've put the soft conversion many places. So this is it's characteristic in compression, but why we use those materials? Mostly for the tensile behavior, which will be around 14 MPa or 2 KSI for a conventional fiber concrete, UHPFRC. So this is what I'm giving you here. For example, on this side, it's UHPC with 2% fiber content, so it can go to stress as high as 14 MPa, or as mentioned here, about 2 KSI. And the beauty about that material is that if we look at the stress strain domain, so you can, once the matrix cracks here, you have a lot of strength and a lot of ductility. So this is what we're using. So if you pull on the series of bars like that in a joint where bars will be lapped, so that puts a lot of pressure on the concrete, and it induces cracking into the material. With UHPC, there's no crushing on the ribs here. It's mostly the tension of the material that governs the behavior. If you look at the normal concrete shown here, you get little confinement or confining effect due to the normal concrete, because the normal concrete has a very low tensile strength. However, with UHPC, you get that very high tensile behavior and ductility, which helps you in providing a very good anchorage. So the anchorage is significantly higher than the confining stress, but significantly higher than normal concrete. So if you do pull on a bar that will be, let's say you pull on that bar here, and you look at what kind of stress you can develop, you can see that for a 8 bar diameter of anchorage, you can go to stress around 60 KSI here, or so you can yield the bar easily for 8 bar diameter and break the bar for a 10 bar diameter for as embedment length. So it's very efficient, and this is for conventional commercial concrete. It's not on the upper high side of this material. So lap splice behavior in UHPC, the way it must be understood, it's welding the bars. If you put 2 bars lap in UHPC, they're welded together. That's the way to see it. And there's no plastic strain penetration into UHPC because the stress varies linearly and goes down quite quickly into the bar. So it's not like conventional concrete. And as mentioned before, if you have the 8 to 10 bar diameter anchorage, it's sufficient to break a normal reinforcing bar with a 2% fiber content of a commercially available UHPC. So that behavior, actually, before knowing everything that I had, about 15 years ago, I had the idea that it could be used to strengthen existing bridges where you have a bridge pier in which will be very very low or very deficient, would be very deficient for seismic behavior. What I did, I just replaced, I had the idea to replace, just remove the concrete in the lap splice region and the normal concrete, and just pour UHPC without modifying anything. Nothing, no additional stirrups, no 135-degree hooks, nothing like that, just to replace and see what I got. and I got something. This is a control column in black here, and my first column actually in red. It was so good that I was not even able to break it because the actuator I didn't have any stroke. And then in the coming years, I look at that the behavior of those the improvement given by UHPC on a lot of columns. However, in that project, I was using 20 bar diameter as lap splice length and 3% fiber content. So it was not optimized. So I thought, if it's working to fix a deficient column, an existing column, could it be used for precast columns? So that was the idea. So the concept is as follows. If you take a cast-in-place column, a simple column, and if you look at the behavior in the plastic hinge region here, the plastic hinge, if you have a not too long column, a short column, will be, plastic hinge will be spread out half and half through, have one half in the footing and one half in the column. This is given by this equation here in SI unit or in American units. Roughly, the plastic string penetration within the footing is roughly 10 bar diameter for conventional reinforcement. And that equation here is the one given by the AASHTO or NHARP and CHARP, sorry, document on to compute the length of the plastic hinge for computing the column behavior. So using that idea, so okay, now if we make precast element in which the bars, so the red bars here are those coming from the footing, and so it's replicating what I had for the existing column, and the blue ones are those coming from the precast element. So they can be lapped like shown here in the same plane, or they can be offset if you want. So if you, when you do design, you can choose whatever you want. Usually for an existing column, they will be in the same plane. For a new one, this one will be preferred. So this is the idea, to put to lap the bar that way. So and as mentioned here, all the pictures are not coming from the same element. So you can see that the bars are not exactly the same from one picture from the other, but you have the bars coming out of the footing here. Then you put some hoops here, and you have your precast element with the longitudinal bars, and then so you just put the two elements together and then pour UHPC, and that's it. That's no more difficult than that. And one good thing is that with UHPC, since you can reach 400 MP or 60 KSI with lap splice of about 8 bar diameter, so you don't need to use hooks at the end of your bars. So it makes the details, you can have much easier details to put in place using when you lap bar in UHPC, whatever kind of bar you have. So to follow the usual way of doing seismic design, so you make sure that your ductile elements here, that the reinforcement at the bottom here that is in the footing, that yields, and you get the ductility from that reinforcement. And for the part of the column that is above the joint, where above the plastic hinge region would be located here, then those elements are protected. So for the same load level, you will remain nearly in the elastic regime, which would allow you to do whatever you want for that element. You can use as long as this element becomes remain in this region, then you make sure that all the plastic deformation occurs at that location. So comparing the two, so the cast in place and the precast solution, so the portion of the plastic hinge, the strain penetration within the footing remains the same. And if you need more, depending on the seismic zone you are and the demand on displacement that you need, then you may have to extend the plastic hinge within the UHPC. However, as I said before, that cannot be done because UHPC, there's no plastic strain penetration in UHPC. So we have two solutions. So if you don't need, if your plastic deformation occurs only in the footing, this is a configuration you may have. But if you want more of the plastic hinge to be going up into above the column, above the footing, then you can use a sleeve and make sure that, so you will increase the length of the plastic hinge here. So our experience says that if there's no debonding, when you compute, you do your computation, then you assume there's no plastic hinge within the UHPC, and if you use a sleeve, then you use that length, and you can select whatever length you want to have to meet the prescribed displacement. So as I said initially, this solution was not optimized for the strengthening of columns. So the first specimen I tested, so we started with a circular column 2 feet in diameter, and we started with the lap length of 10 bar diameter to be just below. I was hoping to be a bit below the target value, so that I could see how much improvement I needed. So, and we picked the UHPC that had that property, and this is very commercially available UHPC in North America, so nothing fancy. So, and the type of behavior we get when we do good tensile stress test on those using the same test setup or similar to that required by AASHTO now, or specified in AASHTO. This is the kind of behavior we get in the stress strain domain, and that kind of behavior in the crack opening domain. So we got that and put that in place. So we had a control specimen and so it took 4 specimens to tailor to come to optimize the design, I should say. So this is the result. We're going to talk about this one. And just to say that these columns were had an axial vertical load, and the percentage of the reinforcement for that column was 2%, which is quite common for seismic application. And this is the type of behavior we got. So the blue curve is the precast one, the red one is the control. So we got actually quite similar results. For a specimen, I wanted to be below the control one. So we were nearly at where we wanted to be. And here we're showing the damage to the column at 5% drift ratio. So we can see that there's spalling in both columns, but so it was expected. So, but if you want to remove, to eliminate spalling, so I'm going to specimen P5 now. So this is the last one we tested as a circular column. So in that one, so we made sure that we used some sleeves just to see how they would behave, and we made sure that the failure, the plastic hinge would occur only in that region here in the footing and within that sleeve, and that we would have no damage, no spalling to the concrete here in the precast element. So that was our target, and this is what we got. So this is the kind of behavior we got with. It's always the same control specimen. The amount of reinforcement was a bit higher for that P5 column, but in terms of behavior, we got a very stable behavior up to a drift ratio of 5%, which was good, and with very little damage, as you can see here in the precast element. And if you look at the usual range for which you would be designing a column, and if you compare the damage to the control column, between the control column and the precast one, there's no damage in the precast one. So it means that after an earthquake, a very severe earthquake for this column at least, this type of design, if you carefully do your design, then you will end up with no damage, no apparent damage, no crushing, no spalling in your precast element, and you will be concentrating all the plasticity and damage without any break, very stable behavior into the plastic hinge region, and will be hidden for, and so you will have a column that won't need repair. So the final concept was validated on the pilot project we just mentioned, that was briefly presented by Dominique before. So this bridge had some architectural feature, because Christophe Colomb is Christopher Columbus, so he sailed to North America. So the architects thought that some sail would be nice. They're not structural, and even the column are too big for that small bridge, because you need a column to be the size to look like something that is robust, but actually they're a bit too big for this. For the size of that bridge. So the specimen tested in the laboratory actually was designed for a bridge that would be more than twice longer than that bridge. So a much bigger bridge that could be, so those columns that we tested were larger, not larger, but had capacity for seismic design for a much larger bridge. So because of the size, this is about 20 feet here, where the lab space is a bit less. So we tested a column that was for that part a bit half, somehow close to half of the actual column size here. So but we kept the same dimension, the same size of the column. So this is what we see here. So we had bars coming from the footing in red, and the bars going into the column. So all the yielding and nonlinear behavior will be in the bars coming from the footing. And we use also sleeves here just because the column we tested was not exactly the one that was built. It's actually much stronger in terms of seismic behavior, and because of the length, because we kept the same length for as the designer, so it was 18 bar diameter, which is a bit too much, but we kept that value for the testing. So it was tested again under axial load and load coming from 2 sets of actuators. So it was tested in biaxial loading for that bridge site. And here I'm showing some behavior of the column during the test. So the test lasted about 6 hours. So we don't work that fast, and but you can see that we went much we went to displacement that was much higher than those required for the pilot bridge, and something that will be, as I said, good for a bridge of a much bigger size. So the behavior was quite good in terms of drift ratio, and the behavior we got in the longitudinal direction under the weak axis direction, a very ductile column. And at the end, it's what you see, although we pushed the column quite far, and there was no damage that could be observed outside the column. So it was in pretty good condition. And at the displacement, the design displacement, there was no visible damage to the column. So did it go well? Because it's UHPC, and so filling the joint, we've done a lot of UHPC mixing in our lab for many columns, many big projects, and so in that case we had, you can see the detail. This is the void that has to be filled, and we had 4 entry points here, so that you can put UHPC on one side and then it flows to the next side, so you can put it and make sure that you fill it up to the top. So this is what. And we ask a UHPC supplier to come and use its equipment and its personnel to do the job. It didn't go very well, actually. It was probably too hot that day in our lab, and it was during summertime. It could be very hot in Montreal during summertime. So the mix was becoming more viscous as the casting proceeded, and at the end we were not able to fill the specimen. So we were quite sad in university, but on a bridge engineer side, I would say it's good thing that things don't not always go well. So we demolished. So our staff, we demolished using jackhammers. We demolished the UHPC such that we could fill it again. So we filled it. So the next batches were done by our staff, and so we were able to repair that bridge and that column. So it went well. So now I'm passing the mic to Dominic for the pilot project.
Hi, I'm going to put some context, project context on our first ABC project, UHPC. It was a project that was planned on a 2-year span, not because of the bridge construction, because we wanted to be using ABC method, but we had a lot of it's a complete project. So we had to refurbish all the retaining wall, do the aqueduct and the sewer, and rebuild the roads. So it was a 2-year project. But and it was also, since it was our pilot project, we didn't want to put any pressure on to put less pressure possible on the company that was going to do the project. So at the end of the project, when we looked at how many days it took to build the bridge, we estimated to be about 38 days of non-consecutive day, compared to one other bridge we built as a cast in place that took 85 days. So we had almost half the time to build those, so it was really faster. So I think that was one of the thing we wanted. One of the context of the project we had is that the code requirement for the Canadian code required that the UHPC gets to 14.5 KSI before it can be subjected to load. And that added a delay of 15 days of maturation for the concrete. So that's one of the issues. Next. As I said before, all of our bridge pieces were all precast elements. So it's all made in at the plant. So it's interesting. It's really fun to be able to do that. The quality control is awesome. At the same time, it's the availability of the precast company that comes to be slowly a problem, since we do much more precast element in Montreal. So companies, if we got to do a lot of bridge with precast element, it's going to be an issue of productivity. So you can see here the footing, the column, and the caps beam or the pier cap that were all precast and assembled rapidly at the company site. Next footage. Next slide. We also cast in play, precast all the bridge element, all the slabs. As you can see, we had some straight slabs and we had some curved slabs. So it was a lot of quality control. You got to be really, really tight with your requirement, and now it's done in on site, but at the same time, it went really well, and it will have been really complicated to do a cast in place for all these elements. How we did pour UHPC on the field, it's a really highly dense environment with a lot of house and people. So we had to use on-site UHPC mixing truck. We didn't bring a permanent mixing plant on the field. And since it was non-continuous day to pour, that was the best way to do it. As you can see, I want to attract your attention, just the slide before, the bags of UHPC are put on the sidewalk, but they're directly exposed to the sun. And that, like Bruno said, in Montreal, it can get to be really hot during summer. So that's going to be an issue later on that I'm going to talk about. Next slide. So you see here is we put the precast footing. We excavated and put the precast footing, and then afterwards we assembled the pier, the pile, the column. So it was really easily done for putting the column up. But as for our experience, the time it took to put the column, the precast footing on the field compared to a cast in place footing, there's not a lot of advantage. So maybe next time we're going to go with a cast in place footing. It's going to be easier to make it fit perfectly in the excavation. So that's one of the consultation we do. Next slide. Now you can see all the joint detail we add at the column base at the cap beam. There was a lot of transversal reinforcement. You see, it's not what we saw in the lab. It was done accordingly to the bridge code, so we got to put the hooks and things like that. So there was no optimization made during design because we hadn't tested the column in the lab yet. So our designer wanted to make it safe, and for us, it was one step in the good direction. So we kept it like that, and it's harder to pour with a lot. So we wanted to see if it was possible. As here you can see, we use the same way of pouring the UHPC in the column base. We wanted the UHPC to flow in the form as to align the fiber in the right direction we wanted. It went pretty well, but as you can see on the right, we had some small cavity where UHPC didn't go. I think it was maybe air that got trapped in the form, or the mix that was a bit too thick. But all in all, we just had to put some concrete, like a small patch of Sika on the column, and it was okay. So it was less of a problem that we had in the lab, but we were ready for it since we already had the problem before. Next column, next slide, sorry. Here you can see we made a good use of our of the many construction cones we have in Montreal. We use it for the cap beam, and it went pretty well. At this moment, we also directed the pores so the fiber in the mix went and aligned in the way we wanted them to work in the cap pier. So that went well also. Next slide. And now that the pier cap was built and the column, we put all of our slab that were precast and we brought it. I was saying that we decided to go piece by piece because it's so dense in Montreal. It's not possible for us to build the bridge and slide it in, and we're not going to be able to do it. So we really go for all of the piece, our precast. So now we connected all those elements on the next slide. As you can see, you got to make your form to be tight, watertight, so that UHPC don't flow under the bridge when you pour it. And also, we use a method that we saw that was used in the United States, in example in FHWA and AASHTO publication, where the joint were cast with a form on the top and with buckets. So we filled the first bucket. When it gets to the second bucket, we fill it again, and we go from one end to the other, and we make sure that everywhere it overflows, so that we make sure that the concrete, the UHPC is everywhere. One of the problems we had is when I talk about the bean bags of UHPC that was stored in the sun, is we started the first pour around 6 o'clock at night. So the temperature had dropped already in Montreal, but the UHPC bag were still very hot. So the first pour were really thick, and we got quite scared when we did it. But it flowed, and we got to the next bucket. And as time went on, the temperature cooled, and the beanbag cooled also. And afterwards, it was much, much easier to pour the UHPC in the joint. So that's one of the things you got to take into account when you do that kind of project. Next slide. We also put all precast barrier wall. We did a lot of design also with UHPC in bridge barrier wall with Polytechnic, but in this one it was more standard barrier wall that were put in place and tied in place. And afterwards, because it was a curved bridge with a good slope, we cast in place an overlay and the sidewalk. So at that time, everything under the bridge was open. So we really opened the road underneath pretty fast. And that's what we're going to do in the next project, because we have a lot of project coming on, and there are more on road that a lot of traffic. So we're going to build the bridge really fast. And with those methods, we can open the road really fast underneath those bridges. And next slides. As you can see, at the end, we have a lot of finishing, surface finishing to do. We want it to be nice, so we put some paint on. We sandblasted and paint the bridges, and we also put silicone anti-graffiti spray, because in Montreal, as you can see on the right, there's already a graffiti on the bridge. And it goes really fast, so we put we put a lot of silicone base anti-graffiti on our walls. And you see in the middle that the wall, before they're painted, there's already graffiti in the construction site. So it's one of the big concerns. But the good thing about the silicone anti-graffiti is it's uniform the surface, and it makes a bit of a wet look. It's not too much, but it gets to be really nice and easy to clean afterwards. Next slide. So when we're at the end of our project, and we had a lot of we learned a lot, and it was a project that was a success. We were able to precast everything, bring it to the field, and join everything with UHPC. But there was still a lot of question on the site, and a lot of how do you say it, DIY. We had to troubleshoot a lot of things. So for the first project, having no pressure to open the bridge really fast was really, I think, the way to go for us to learn and to have time to solve all those projects. It's like it's written. It's a really good step on the learning curve. But we found out that there's a lot of things that can be better on our next project that is at the moment in Arukit. It's on the market for to find a construction company to do. So we went for a simpler design of reinforcement as we tested in the lab. So we're going to have less problem filling all those void, and also the joints in the slab to go with smaller rebar to join the slab deck, each piece of them. We got to make a lot more meeting to get information across to the company, the people on the field, the site supervisor, so people are really, how you can say, are really prepared to do that kind of project. All of the participants on the field, they were talking about UHPC. UHPC, it's concrete. You got to have a compression strength. So it's really a concrete world. And what we try to teach them is we use UHPC, okay, for compressive strength, but much more for its tensile strength. So quality control, it's okay to test for compression, but we need to have quality control to test tensile strength. And that's going to be really, really important for the next project, because we poured concrete, and then we got to take some samples and to make sure that the pour is the right way, and that the fiber works in like it was designed to do in tensile strength. We got to have a lot more mock-up of our element that are identical to those that we're going to pour in the field. So we're going to have mock-up element that's going to be poured on site, but before we do the real thing, we're going to cut them up. We're going to look at the fiber orientation, things like that. We're going to have more information in our document to help everybody on the field. We're also going to debrief. We're going to do a debrief with our site supervisor and everybody to be more, to have a better project next time. And each project, we have that post-mortem, we call it, is at the end, we debrief everybody working on those projects to make our next project better. So it's going to be like that. We also are going to have training that's going to be given by Polytechnic for our in-house engineer, and also site supervisor, and all the people involved in those projects. And so we're going to transfer technology from university to the city, and the people, and we got a lab in our city that is really got expert in concrete, so they're going to be trained, and then they're going to be able to train our external labs also. So it's going to be easier for them to make supervise the construction site, to make sure that everything is great. We're going to control temperature better. We're about the bean bags of UHPC. We're going to put it in the shade. And also, one of the things that was a problem is the code asks for 100 MPAs of compression before we can put construction load. And that's really takes a long time for UHPC to reach those, and you have some control concrete that you test in the lab, and it's a lot of back and forth. And I think is what we want with UHPC in those kind of application, it's tensile strength. So compression is okay, but you need to be able to test compensation, tensile strength. So we're gonna try to have curve from compression to tension with our test of tension in the field. So we're gonna be able to put contraction load faster, and those loads are gonna be, and the material, UHPC material, will be at the strength needed for those loads. And don't wait for 100 MPa, because we could have cut the construction time of this bridge by, I think, 10 days. So it may be 30 days and not 40 days. So it gets to be much more ABC. So that's about all the lesson learned I add on that project. If you go to the next slide, I think it goes back to you, Bruno.
Yeah. Thank you, Dominic. So to finalize that presentation, so on the technical side, UHPC lab splice region for seismic application, I think what we have learned over the last 20 years or so, and particularly the last few years for ABC, I think all design principles are well managed. Publications are coming, but I think there's we're more at the validation side or validation aspect of if someone wants to test something else or to design something else, and the equations and methodology for designing are coming. It's not in the code yet, but the knowledge is there, and I think it's more at least for that type of ABC application for bridges, accelerated bridge construction. I think we're more at the validation stage now. The as I mentioned, anchorage in UHPC, it's something that is not, there are no equations yet, but the work we've been doing in parallel to those full big column project, there's been a lot of research about the how to have a better understanding on the how anchorage and lap splice work in UHPC, and that is well managed now, and publications are coming as well. So as Dominic mentioned, the City of Montreal is planning for a similar project in the very near future. And on the research side, I'd like to acknowledge those supporting agencies and companies who helped us to bring that project, and of course all the people that worked, many graduate students and people from company, and we're ready for your questions. Thank you.
All right, thank you, Bruno. Thanks, Bruno and Dominic, for a very interesting presentation. Good example of going from research and implementing in the practice. So at this point, we're going to turn it to Paul Lives, formerly with Georgia DOT, and Rick Leptic with Michigan DOT, to moderate the question and answer period. Paul?
All right, well, thank you to Torrid. And Bruno and Dominic, a real interesting presentation. We do have some questions that have come in. We'll go ahead and get into the ones that came in pre-webinar. The first one here is they asked, would this webinar present some applications using UHPFRC?
Yeah, so as I mentioned throughout at the beginning, UHPFRC is more the European way of talking about UHPC. So UHPC and UHPFRC, at least for me, this is the same thing. So they're the same material, as long as you put fiber in UHPC.
Okay. Another question that came in pre-webinar was, does this research have applicability to railway bridges? And since schedule is a critical element for railway bridge replacements.
Yes, it does, and actually, it's applicable to all type of. We applied it for bridges, but it could be applied for, of course, for railway bridges, and also for other types of construction where precast, which involves precast element that you want to connect together. I know it's been used for building metro, a subway station in Montreal, things like that. So yes.
Okay. Would there be, this one came in beforehand, would there be any challenges meeting code provisions related to joint shear capacity and adjoining capacity protected elements?
Yeah, this is a good question. I don't think there's an issue, but for the person who has that question, maybe they could join me, maybe explain in more detail what are the concerns. But of course, we have not had any such a problem in everything we've done, but there might be some issues that maybe we haven't seen. So I would be pleased to answer that question afterward. Yeah.
Okay. We had a question here on what is the unit cost of UHPC per cubic yard or cubic foot?
In US dollar and in cubic yard, I would say it's a bit tricky. It's more okay. I'm not in the construction business. I get it for free mostly, or nearly free. So I'm not paying. But I would say that what I've heard is people are saving on the construction. Yeah, the material may be expensive, but at the end, if you're the way you build things and if you use it properly, usually it comes. During construction, and it's been the experience in Europe. What I've been hearing is that at construction, it's you come even, so compared to conventional. But I think the better you are in designing, optimizing, the better the cheaper it is.
Yeah, when we did the pedestrian footbridge that I showed at the start of my presentation, is one was built beside, that was with a concrete slab, and the other one were with UHPC slab. And we know that the product is more expensive, but when we look at those two projects, cost-wise, on the project side, they're both the same price. Even when we went and on construction, it's about the same price. But we know that we're gonna save a lot of money on durability, on life cycle analysis. So I think we got to stop focusing on the price of the UHPC, and we got to focus on life cost analysis. If we don't need to come back in 30 years, and that's the problem I have. I have 300 bridge, and I got to take care of them all. If I come back every 30 years, I won't be able to do it. It costs a lot. But if I use UHPC and good material, and I come back every 50, 60 years, it's going to be better. So I think you got to focus on the life cost analysis.
Okay. One more question here that came in pre-webinar. It says, is it possible for the plastic hinge to shift inside the column? If so, would this result in increased shear demand?
Yeah, actually, the beauty about the UHPC, what I showed you is something that is similar to the cast-in-place construction. But if there are many various ways to design that plastic hinge region so that you can select where it will occur, and it will be more in the footing. You can put the UHPC in the footing. So there are various options, and yes, so there's little chance that it will shift according as if I answer the question toward the column, but much more you can select exactly where it will occur. So you have much more control with this approach than you would have with conventional cast in place.
Okay. Some new questions that came in. The first one I have here is, with the amount of drift allowed without any damage, is there any concern with compatibility to the remaining structure, such as maybe the gravity system?
But the drift is what there's a target drift. So the drift we got everything. If you look at textbook, people push the column to 4, 5, 6% drift ratio. It's what we do in the lab. When you do your design, you select the drift. For example, if in a given project you need a drift ratio of 2%, then you design for that. But your design, if you're following the code for cast in place, for example, but it's the same for the precast element, then of course your column will be able to sustain, should be able to sustain larger drift. It doesn't mean that it will go as far as it goes where the earthquake brings you.
Okay. Here's one that says the sleeves on the bar allow for plastic movement. Is there any concern that the damage to the bars will be hidden by the sleeve concrete?
It's a very good question. Yeah, there's no damage because I mean it yields. It goes to strain hardening, but it's the same with every steel element in concrete and bar and steel structures. You want, when there's an earthquake, the steel yields but remain intact. And usually, if you do a good design, you will, the steel, the reinforcing bar will remain in the range where you will be no damage after a major earthquake. I mean, there will be some left deformation due to the classification, but beyond that, it's I would say the beauty of it is the amount of damage will be no more than what you would see in conventional design using cast in place. The beauty is also you can select where it's going to happen and which part is going to yield. So you get a much better control on your design using a combination of UHPC and sleeves. What I propose here is just it's model number one. Yeah, that can be improved in different ways depending on which design, target, displacement, and behavior you want to have.
Okay. Here's one. Could you use vibrators or vibrating forms to eliminate the voids in the UHPC joints?
Well, yes, you can, but you have to be cautious not to over vibrate it. So usually, if you have a good design, a good mixed design can flow, and you let it flow. However, and it happened in our lab, and it can sometimes you may have the UHPC may become a bit too sticky, too viscous, so the viscosity is a bit too high. So you can put a vibrator away, or either in the form of what we've been doing sometimes to put a needle, but not into the formwork, but in the cone, just where you put your concrete, just to put some slight vibration there, and you see that the UHPC starts to move. So, but don't over vibrate, just to give it another swing, so that if it stops, just swing it, shake it a little bit, and then let it flow. The more it flows naturally, the better it is.
Okay.
And you don't want segregation. That's the thing. If you vibrate too much, the fibers would just go down into your mold.
Yeah, we had for this project on the slab, on the bridge slab, we had some slight exterior from the underneath vibration, but just slight. We didn't want to have segregation, but at time we saw that the flow would slowly get slower, so we put some energy back with some vibration, but just a little bit.
Okay. This next one's a little bit long here. It says, can you describe the material quality control measures used for using HPC in your projects? And then what fresh property tests are performed to test for a quality mix? And finally, are there any tests performed afterwards other than a compression test?
You want to talk about that project? I can answer about what we do in our lab. In that project, the quality control, as Dominic said, was not the best, but what we suggested, what we do in the lab, in our lab, when we pour, we just we make sure that the workability, the fluidity is right. So there are some, and we follow the what the FHWA has written in their many documents, and the Canadian standard are the same. So we follow what are in the code so that you get a good workability, so that you can pour, and usually it flows slowly, but it does flow. So so this is for the wet mix. For the quality control after, for the hardened UHPC, there are still some issues. We know the answer, but the practice, the field practice, is not yet to the, I would say, the scientific knowledge we have now in our in some universities or some research groups. So you can do a very good bending test. There are two tests that I'm recommending. Is an anchorage test. If I I don't know if I still have control of my presentation, but if I go very quickly to a test, this test has been used. We call that DTB. We name it that way, and we're not the only one who are using that test. But we made sure that that this test actually we came to a standard type of specimen. So this type of specimen can be cast on the site, and then in the lab later on, you just can pull on those central bar here, and that bar is a bit shorter. So this is the bar that breaks. This is a test that has to be done, according to me, before when you design your HPC. When you it's an information that has to be given by the supplier, and you cast a few of those during your construction. So this is an indirect way to test the tensile behavior of UHPC. So this is one way. The second way is to cast some prisms to do bending tests. But in all cases, and this is where there's a lot of issues, if those specimens are not cast correctly, and there are ways to cast them correctly, then what you will get is something that is lower than what you would expect, because in the casting procedure of those specimens that are used to test either in bending or in bound here, they both are testing the tensile behavior, then you're gonna run into some legal issues because the strength won't be there. So to make a long answer short, yes, it's feasible. So it's either Anchorage like DTV test, and I could provide. Quebec Ministry of Transport is implementing that type of test to pre-qualified mixes now, and this test could be, you just have to make one of those tests, a few of those tests in your trial, when you do your mock-up prior to you do those tests, and that will tell you if the HPC you have is the right one.
Okay, were there any tests you did after it was poured,
Yep.
other than the compression test?
Yeah, well, like Bruno said, that what we're going to do in the future. What we did in the field is we tested for workability. Also, we tested for the mass of fiber that we put in the mix, because it was with a on-site truck. So we tested the amount to make sure that we had the prescribed amount of fiber. And afterwards, we took some concrete specimen to test for compressive strength. But on the start, but as the project went along, we took also specimen for anchorage and some bending. And now we're going to work with Polytechnic to transfer the technology from university to our city lab. So we're going to be able to make it in-house, test those, to be able in the next project with a mock-up to test before we pour that the material we use is the same or as the minimum tensile strength that we want in design. So it's like concrete. You want to have a column with 35 concrete, you're going to test it. If you want to have some tensile strength, you got to test it. So we're gonna implement it in our next project next year. So, and we're gonna test what we add at that project at the same time, but we haven't had the result yet.
Okay, we have one here. It says they will run to elaborate some on the lessons learned and relating to the elevated temperatures and the fresh state UHPC. In particular, what measures were taken by the producers to avoid such issues? And then he goes on and says there's quite a bit of information discussing this, control of mixing temperatures and ensure satisfactory temperature of the mix a couple of hours after, for a couple of hours. They were wondering if planning of the pours might actually have been the main contributor to this issue.
No, we had ice. We had planned to be later in the day. We controlled the temperature. But when you take the mix and you bring it and you start to put it in the form with the concrete, that is also hot. We had some problem. And as the sun went down and the temperature cooled, it was better. But for sure, we're going to improve on our control of it, because we saw that one of the problems, the beanbag were pretty hot. But when we mixed, we controlled the temperature going out of the truck. But afterward, when we pulled it, we had to put a lot of ice and things like that. So I think we can do better. And we saw that during the rest of the day, it was getting easier. with the same thing. So we're still troubleshooting, and it's something that is not used a lot, and we want to be a success. We don't want to fail when we do those things. So we're gonna improve our design specification for sure.
Okay.
But I could give more information if the person wants to contact me and see.
All right.
With pleasure.
Getting to be about 10 after. I'm going to call Rick in and see if he wants to pick up. There's a few more questions here. Rick?
Yep. Hi, Paul. Thanks.
Yeah.
Got a couple questions here. One was, and I heard you say this earlier, was, elaborate why UHPC is not concrete. Obviously, it's a similar looking material. It gets hard, and I guess you've made that comment a couple of times. So.
Actually, once it's not concrete, actually, just to make people realize it's concrete of the on the upper hand in terms of its technology. So you have to be cautious the way you place it. And normal concrete, it took probably decades so that people were able to do good in-place concrete, especially when we went up to the higher strength. The same with pre-stressing. There's like when you have it's a new technology. That's why I'm putting that this way. It's a new technology, so you don't use. You have to train people to say, okay, this concrete, because it's a concrete, but it's not the normal concrete. It has its way of being in place.
Yep. Has its own nuances, right? And you got to think about it differently. Yep.
Yeah. So it's a new technology. Why when I say it's not concrete, because people think, oh yeah, it's like concrete. I've been using concrete for 30 years. I know how to do. No, it's why in Europe they call it cementitious composite. I prefer to use concrete. It's shorter, but it's a different material.
So in that, did you have to do any, between the precast where you poured the joints in, did you have to do any kind of special treatment to the concrete on that, where the UHPC bonds to the precast units?
Oh, it bonds quite well, actually. You have a very, very extremely good bond between the concrete, the precast element. If you want to improve the bond, because you may need, if it's a important aspect to have something that is more than usual, then you can have support some retarder or things so that you can expose the aggregates on the precast elements if needed. But I guess each application has its own requirements. But usually UHPC is a sticky material, so its strength. So if there's something that has to be to break, it will be on the precast element side if something breaks in tension if you pull on it. So it's not at the interface, actually. It's a bit behind.
Away from it. Okay.
Yeah.
Was there anything, especially in this kind of situation, was there any special consideration to protect the joints from corrosion or any kind of infiltration? Because obviously it looks like you're down in an area where there's a lot of maintenance activities going on. So.
Dominic, maybe.
Yeah, yes, it's me. I pushed on the wrong button. Yes, on the base of the column, we put some wrapping to get it watertight on the joint, just to make sure that, because also we had a small gap to fill with cement grout, so we put some wrapping. On the bridge, there was a concrete overlay, and afterwards going to be some. We put a membrane and we put some asphalt. So we had that. And under the bridge, usually we don't have that kind of problem. It's more at the base of the column and on the top of it. So with those protection, we're pretty sure it's going to be good. But we're also monitoring the footbridge, the pedestrian bridge, where we had joints that are exposed. So and those are really exposed. So we're monitoring them and seeing how they age. So it's going to be a lesson learned from that project also.
Yep. So kind of, Bruno, you mentioned earlier, just a minute ago, about and my question is, does UHPC have admixture options that would assist the workability of it?
Yes, it does. And you can increase the workability, you can decrease it. Also, you can make it thicker if you want. For example, if you pour UHPC on a slope, something then or an element that is not horizontal, then you want the UHPC to remain on that surface. So you can adjust the viscosity of that material. I have to be honest, I'm not a technologist type in UHPC. I'm buying what people are selling, so buying or ordering. So I'm a more structural engineer. So I said to the supplier, I want a UHPC that has this and this characteristic. Can you give it to me? And I follow their recipes. So I don't know exactly what are product A, B, C that I'm adding to the mix. I don't know what they do, what are their name, but as long as they do what they want, I'm pleased.
Because I know a couple times, or some of the things you mentioned was trying to get the fibers to go in the right orientation. And I guess, how do you, just curious, how do you make sure that what do you do to make sure you get the fibers are just there, right? But at the same time, you mentioned orientation.
Yeah, it's a very good point, and I just finished. I just had a master student to finish a project in which we measured a lot of those joints. We tested specimen coming from different locations in those joints, and I would say to make a short story, where you put UHPC, the entrance location, you get. It's the worst place where the fibers are oriented in a random direction. So you get the least performance at the entry point and at the end of your formwork when your flow ends and you cannot control. So I think the best way, especially for if you can pour at many locations but are not too close to each other, let's say like if they can be, and depending on your material in each case, but if they can be a few feet between each of them, so in between the two entry points, you can assume that the fibers and the mix will be in the right direction. And my answer is for when you have bars that you want to anchor. Okay, so for the joints, for the anchorage in a beam, if you have a precast beam, that could be different. But and there are ways now. Some people may think it's the university level research side, but yeah, there are software now that are coming and we're using it, and where you can kind of predict or have a good idea how your fibers will be oriented, and it's I would say it's at the research level, but I would say in a few years it will be. And when I say a few, less than 5 years, the technology is there, the knowledge is there. Just to what's needed is the to make to validate that when you compute something and you're using your software and you this is what you predicted, is what you got. But we're at that stage now, and I don't think it's why, however, that and it's a point that is important, that I showed in a slide, I don't know, around slide 12 or something like this, I showed some very high tensile strength of UHPC. This is the ideal case in a 2x2 bar, okay, in which you pull. So in that bar, all the fibers are oriented in the right way. So this is the upper end. In your structure, you get something that could be a third of that in terms of strength, and because you have less fibers, it won't be oriented the same way. So it's why in each of the codes, and FHWA and AASHTO, they're working that way. CSA on our side and the Europeans as well, is to have factors that say, okay, if you pour that way, this is what you're gonna get, and this is the factor you should be, the strength reduction factor, for example, that so that you could, in your design, pick the right number. But to maybe conclude on that, the technology of using UHPC for structural application, we're past the infancy of that technology. We're more in the teenage period now. So teenage, I mean, it grows. Sometimes it grows too fast, but we're coming toward a more mature technology, and the more we use it, the better we're becoming. Maybe like the city of Montreal did, start with a small project and don't try to go to the big home run for the first time. So just a little bunt at a time.
Yeah. So kind of looking at there's a question here with multiple parts here. It says, can shear be a concern at the interface between the column and the foundation? I guess
In our
probably
case, it has
because
not
of the
been
different materials, maybe, or something. But that's
it
it
has
seems
not
like
been
that shouldn't
has
really
never
be an
been
issue. Yeah.
that has never been an issue unless there's something maybe the question they think about something that was not tested. So, but at least what we tested, and we tested, I just showed you 6 columns, but when we did the strengthening of the column, we tested 12 large columns that were 15 feet high and huge columns, full size, and
Yeah.
but that has never been a problem.
There was a question here about the construction tolerances of precast elements. I'm assuming just for this, it's the same as any other precast units. So, and then what type of connection is used for the pier to cap at the top? Or if because it looked like you had precast pier cap going across, right? Was there or was that cast right with the stem going up for the column or for the for the column?
That I'm not sure. I don't know if Dominic was.
No, I'm not sure. I would have to look into.
I think it was more a conventional connection because that small bridge actually was not designed for seismic, so it was designed elastic. So the seismic was not. I mean, for that one, because the columns were so big, and so I guess it was not. So the seismic loads are very small for that bridge. Yeah.
Okay. Let's see, I got one other here. Bridge exit using UHPC boards and let's see. I would like to know your opinion whether it is possible to reinforce an existing bridge pier using precast UHPC boards, enlarging the pier dimensions. So I guess, it's a kind of a retrofit type thing.
I think we have time maybe for one more question, and then so we can wrap it up.
Okay, sounds good, Henry. Let's see, plastic hinge column interface at 10D or more, how large is the displacement of the column? So kind of asking that question about the interface with a plastic hinge. If it was at 10 LD or more, how large would the displacement on the top of the column be?
The embedment length has nothing to do with the plastic hinge does not occur in the UHPC. So the plastic hinge only occurs in the conventional concrete. So you get the displacement you get is the same as you would get for cast in place for the part of the bar that is the normal concrete. And if you want that displacement and when you compute, for example, in your and it's described in many textbooks and Priestley and many other ones. So the LP, the length of the plastic hinge, you can compute the displacement using that value. And so the beauty with the sleeve that we use, you can select the length of the plastic hinge according to the displacement you want to reach in your. I'm assuming that people are doing displacement-based design with a target displacement. You want to reach 6-inch displacement at the top, then you know the rotation at the base, and so it's a textbook type solution. It's not more complicated than that.
Yeah. Well, thank you, Bruno and Dominic. It was a great presentation and subject, and I'll turn it back over to Adirad now. So thank you.
All right, thank you. Thank you all. Thank you, Bruno. Thank you, Rick, Paul, and Dominic. Great presentation, very informative. On that note, we are going to conclude our webinar and hope to have you back with us for our next monthly webinar, which will be on February 20. So long.
Bye. Thank you very much. I appreciate for your invitation and your attendance.
Thank you.
Thank you.